All right, let's dive into one of the most powerful and honestly one of the most beautiful laws in all of physics, Gauss's law. Now, I know it's a cornerstone of electromagnetism, but it can feel a little abstract, almost like magic. So today, we're going to demystify it, and we'll do it by looking at something you've definitely experienced, something that shows just how much this law shapes our world.
You know the feeling. You step into an elevator, the doors slide shut, and boom, your call drops. Your internet connection just vanishes. That's not a coincidence, folks. That's pure physics in action. So what is actually going on inside that metal box?
Well, the key to unlocking this little mystery was figured out way back in the 19th century by an absolute genius of a mathematician and physicist, Carl Friedrich Gauss. And his law, it gives us this incredibly profound way of looking at the relationship between electric charges and the invisible force fields they create all around them.
But, before we can really appreciate the elegance of Gauss's solution, we got to understand the problem he was trying to solve in the first place. And that whole problem starts with electric fields.
So every single electric charge in the universe, from the tiny electrons in your phone to the massive protons in the sun, it generates an electric field. You can kind of think of it like an invisible web of influence that stretches out into space. Now, if you want to find the total force on any one charge, you have to add up the influence, the push and pull from every single other charge around it.
And this is exactly where the frustration kicks in. See, if you use the traditional method, which is called Coulomb's law, you literally have to calculate the field from every charge and then add them all up as vectors. For anything more complicated than just a couple of charges, this becomes an absolute mathematical nightmare of integration. Physicists knew there just had to be a better way, a shortcut for the right kind of problem.
And that shortcut, it comes from completely rethinking the problem. Instead of painstakingly adding up forces, Gauss had this brilliant idea. What if we just counted invisible lines? This core concept is something we call electric flux. Okay, imagine for a second that we can actually see these electric field lines. And let's say we draw an imaginary bubble, a closed loop, around a part of that field. Now here's the cool part. If there's no charge inside our bubble, for every single field line that goes into it, another one has to come out. The number of lines flowing out is perfectly balanced by the number flowing in. So the net count, it's zero, always.
But watch what happens when we move our shape to actually enclose a positive charge. Now we've got lines that are starting from inside our bubble and flowing out in every direction. And all of a sudden we have way more lines going out than are coming in. We've got a positive net count of lines flowing outwards. It's such a simple visual way to get the core idea.
So this whole net lines out idea, it has a formal name, electric flux. It's really just a way to quantify how much of the electric field is piercing through one of our imaginary closed surfaces. It's simple. More charge inside means more field lines starting inside, which means more net flux. And this brings us right to the law itself. Put simply, the total flux, our net count of lines, is directly tied to the total amount of charge you've trapped inside your surface. And here's the really wild part. It doesn't matter where that charge is inside the surface or how it's spread out, the relationship is absolute. That, right there, is the magic of Gauss's law. Now, this law is always true, but, and this is a big but, it's only really useful as a calculation shortcut under one very special condition. To turn that awful calculus into simple arithmetic, we need a superpower, and that superpower is symmetry. Let's see why that is. If we try to surround a point charge with an imaginary box, what we call a Gaussian surface, well, the field lines are going to hit that surface at all kinds of different angles and distances. The field strength isn't constant across the faces of the box. And just like that, we're right back to doing complicated math. The shortcut just doesn't work.
But what if we choose a surface that perfectly matches the symmetry of the charge? Like a sphere around a single point charge. Now everything changes. Every single point on our spherical surface is the exact same distance from the charge, so the field strength is constant everywhere. And the field lines, they're perfectly perpendicular to the surface at every point. That horrible complex integral just became the field strength times the surface area. It's just simple multiplication. That is the power of symmetry.
And hey, if this feels like a tricky concept, don't worry. You are not alone. As this user from a physics forum points out, figuring out when you can and, just as importantly, when you can't use Gauss's law as a shortcut, well, that's one of the biggest hurdles in really understanding electromagnetism. It's not a magic wand you can wave at any problem. It's a very specialized tool that works wonders on symmetrical problems.
All right, so now that we have the tools, we understand flux and the power of symmetry, let's go back to where we started. It's time to solve the elevator mystery.
Okay, so an elevator is really just a big metal box. In physics, we call that a Faraday cage. When the radio waves from the cell tower, which are really just traveling electric fields, hit the elevator's metal shell, the free electrons inside that metal start to move around. They literally rearrange themselves, and in doing so, they create a brand new electric field that points in the exact opposite direction. And here's the crucial part. This new internal field perfectly cancels out the external field from the radio wave. The result? The net electric field inside that metal box becomes zero. No field, no signal. And we can explain this perfectly using Gauss's law. Think about it. If we draw one of our imaginary Gaussian surfaces anywhere inside the conductive walls of the elevator, that surface isn't enclosing any net charge. So what does Gauss's law tell us? If the enclosed charge is zero, the total electric flux through our surface must also be zero. And for that to happen, the electric field itself has to be zero everywhere inside. You see, Gauss's law doesn't just describe this effect, it fundamentally predicts it.
So we've seen just how powerful Gauss's law is for electricity. But you know what? The story doesn't end there. This law has a twin in the world of magnetism, and it hints at a really deep mystery about the fundamental nature of our entire universe.
So Gauss's law for magnetism is deceptively simple. It basically says that if you do our line counting exercise for any magnetic field, the net flux through a closed surface is always zero. That's just a very scientific way of saying something you already know. You can't isolate a north pole from a south pole. If you cut a magnet in half, you don't get a separate north and a separate south, you just get two smaller magnets, and each one has both poles.
But what if you could? What if a magnetic monopole, a particle that's just a north pole or just a south pole all by itself, actually existed? Physicists have been looking for these things for decades. We've never, ever found one, but our theories suggest they could be out there.
And the implication of finding one is just profound. This table shows Maxwell's equations. These are the 4 fundamental rules that govern all of electricity and magnetism. The equations on the left are the ones we use every single day. On the right, that's how they would have to change if we ever discovered a magnetic monopole. Just look at Gauss's law for magnetism. It wouldn't be zero anymore. It would become perfectly symmetrical with its electric twin proportional to the magnetic charge inside.
Think about that. Finding just one of these hypothetical particles would fundamentally alter our understanding of the entire universe. It would mean that one of the laws we thought was absolute is actually just an observation based on an incomplete picture. It would be one of the biggest discoveries in the history of science.
And that really leaves us with a final, mind-bending thought. Gauss's law is so incredibly powerful. It explains everything from a dropped call in an elevator to the ongoing bleeding-edge search for exotic particles. But it also reminds us that science is a journey, not a destination. The rules we've written down are our best description of reality so far. It makes you wonder, what other fundamental rules might be out there, just waiting for a discovery that changes everything?